Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be proving the chain rule of differentiation. Last time we saw that if we have two differentiable functions, or rather two functions which are right differentiable at a point A which is not the right boundary point of the interval, then the sum of the two functions is also right differentiable at that point, and the right derivative is given by this simple formula. The product has the same story, except the formula for the derivative is a little bit more complicated. And if in addition g does not vanish anywhere on the interval, then the ratio of f and g is well defined, and its right derivative behaves in this way, in fact, meaning that this is right differentiable at a and the right derivative behaves in this way. And then we saw an application of these things to these kinds of functions. If we have this function, then it is differentiable everywhere, and the derivative itself is a function which I want to emphasize, and that function is given by this formula. So the derivative at any point x is given by this. Alright, and then we saw that if you have a polynomial, then you can use these rules to calculate the derivative of the polynomial at any given point. Okay, so now these are the problems, and let us state and prove the chain rule. This is going to be a short lecture. So we have a function function f defined on an interval I, and a function g defined on an interval j, and assume that the image of f is contained in j. Thus g composed f makes sense, and it is a function from I to R. All right, and now let a and I be such that f is, so let me make 2 points such that f is right differentiable at a, g is right differentiable at f of a. So when I write these two things, I already mean that a is not the right boundary point of I and fa is not the right boundary point of j. Then the conclusion is that the composite is right differentiable at a, and the right derivative can be calculated by this formula. So the formula is the right derivative of the composite at a is the right derivative of g at f of a times the right derivative of f at a. And again, I am proving everything for right derivatives. You can prove the same thing for left derivatives and for differentiable functions, where instead of all these subscripts, you won't have these subscripts. It will be much neater looking. I'm just perhaps needlessly being too general. Anyway, so now here is the thing. So we showed that since f is right differentiable at a, we can find a function a from I to R such that a is right continuous at a, and f of x minus f of a, perhaps we don't even need this. Okay, fine. So I actually don't need this one. I need the other one. So since g is right differentiable at f of a, and let me write f of a as b just for notational simplicity, we know that there is a function b going from j to r such that B is right differentiable at little b, and g of y minus g of b equals b of y times y minus b for all y in J. So this we showed. This is the one of the analytical characterizations of differentiability, right differentiability. So now what we want to really worry about is this limit, which is g composed with f evaluated at x minus g composed with f evaluated at a divided by x minus a. We want to show that this limit exists and is equal to whatever is stated above. So, well, this limit is nothing but by this formula. This is g of fx is, okay, so let me not skip anything. This is g of fx minus g of fa divided by x minus a, which is, now we use star, let me call this star. So this is where we use star. We get g of p plus p of fx times f of x minus p, right, and minus g of f. So f of a is b, so I will write that as b. So this f of a is b, and the g of fx is all of this nonsense which is coming from here. So these two things cancel off, and we are left with b of fx, f of x minus f of a divided by x minus a. So here I have substituted b as f of a, and let me write a better typesetting. This is b of fx, and let me just do one more massaging, this notational massaging. It is b composed with f of x. So we wanted to show that this limit exists, which boils down to showing that this limit exists, but these individual limits exist. This one exists simply because f is right differentiable at a, and this exists because since f is right differentiable at a, f is at the very least right continuous at a, and b is right continuous at f of a. And here I have made a typo. B is not right differentiable at b, b is right continuous at b. So please note I made a typographical error here. Okay, so again, so f is right continuous at a because it is right differentiable at a, and b is right continuous at f of a, and therefore the composite is also right continuous at a. So this means that this limit is actually this product of limits. Which is b of fa, the other one is this guy, which is g, right derivative of g at fa. right? This is how b was defined. If you take the ratio and take the limit y going to f of a, you will get that the derivative of g, right derivative of g at f of a is b of f of a. So that therefore we have this. So a very simple proof, except that here what one would naturally would like to do is something like this. Let me just make a remark here. Instead of using this, one would have naturally liked to perhaps use this kind of a algebraic trick. So you multiply and divide both numerator, multiply both numerator and denominator by this expression. So what we have done is we have multiplied the numerator by this and the denominator by this. So this is equal to that. But there's a slight problem with this, because this may become 0, then we would be multiplying the numerator and denominator by 0. And even then it is not completely clear what to do, even if that issue was not there. So one can perhaps get a proof by using this kind of trick, but it's just better to use that. Anyway. So that's that, and now let us look at an application. A very, very simple application. In fact, this I've already given as a problem. In fact, in this particular lecture, this problem appeared in the beginning. So what I want to argue is the following. So let f be a differentiable function and n be a natural number. Define as gx equals fx to the power n for all x. Then the derivative of g at any x is given by n fx to the power n minus 1, the derivative of f at x. Okay, so let's see how to do this. You can do it using the product rule, as I have hinted in the problem above. But here is another way to do it. So let phi be defined as phi x equals x to the n. Then g is nothing but phi composed with f. Right, very simple. And therefore, since phi is of course differentiable, we showed it in the last lecture, it is after all polynomial, so it is differentiable, and we know how to compute its derivative. F is also differentiable as given in the hypothesis. So this g guy is also differentiable, and therefore by chain rule, g prime x equals phi prime fx f prime x for all x in R, which is, so what is phi prime of fx? It is n fx to the power n minus 1. This is how polynomials are differentiated, and f prime x. So that's it, that's what we wanted to show. So sometimes if you want to calculate the derivative of something, then it is fruitful to recognize the given function as composites of some simpler functions, and that's what we did here. So chain rule is very useful. So far we haven't developed a big collection of functions that are differentiable. The only functions that we know, concrete examples of functions that we know are differentiable are so far just polynomials. So as we go along in the course, we will look at more such functions like the trigonometric functions, the exponential, logarithmic functions, those kind of square roots, those things. But that will take some time. These trigonometric functions will come when we will do infinite series and whatnot. So that will take some time. Okay, alright. So as usual, like, comment, share, subscribe. Also have Patreon. The link is in the description below.